Now, let us discuss the work energy theorem. That is, we want to derive a relation between work and energy. According to work energy theorem, the work done is equals to change in kinetic energy. So let us prove that. We know the Newton's third law of equation, that is V square is equals to U square plus 2AS. Now multiply both the side by half m. So this will be half m V square is equals to half m U square plus half m into 2AS. This 2 will get cancelled out, so we will get half m V square minus half m U square is equals to this mass into acceleration is force, so F into S. But we know that force into displacement is equals to work done. So we can write work done is equals to half m V square minus half m U square. V is the final velocity and U is the initial velocity. So in that case, half mv square will be final kinetic energy and half mu square will be initial kinetic energy. So work done will be equal to final kinetic energy minus initial kinetic energy. So that will give us work done is equals to change in kinetic energy. So this is the work energy theorem. Let us now see one example based on the work energy theorem. In the example, it is given that a raindrop of mass 2 gram falling from a height of 1 kilometer hits the ground with speed of 40 meters per second. We want to find the work done by gravitational force and work done by the air friction, given G is equals to 10 meters per second square. Here, initially, when the raindrop is falling, it was having some energy. So, initial energy, let's say EI, is equals to mgh. So mass is 2 divided by 1000 because it is in gram into 10 into 1 kilometer, that is 1000 meter. So the initial energy is 20 joule. Now when it hits the ground, it is having some velocity, so final kinetic energy will be half mv square, that is equals to half mass is 2 divided by 1000 into v square, that is 400. That will give us the answer 4 divided by 10 joule. The speed was 40 meters per second, so this will give us 40 into 40. So the final energy will be 1.6 joule. Now it should have the energy of 20 joule, but it is having energy of 1.6 joule. So energy lost due to friction is 20 joule minus 1.6 joule. This will give us the answer 18.4 joule. So work done by friction will be equal to 18.4 joule. Now we want to find the work done by gravitational force. Work done by gravitational force will be force into displacement. The force is mg into displacement. Mass is 2 divided by 1000 into g is 10 into displacement, that is 1 kilometer, that will be 1000 meter. So work done by gravity will be 20 joule. Now let us see work energy theorem for a variable force. The kinetic energy is given by half mv square. Differentiated both the side with respect to time, we will get dk by dt is equals to d by dt of half mv square. Here half and m are constant, so we can write dk by dt is equals to half m d by dt of v square. So dk by dt will be equal to half m 2v dv by dt, but dv by dt is equals to acceleration. So we can write dk by dt is equals to half m 2v into acceleration. This 2 will get cancelled out, so we can write dk by dt is equals to mav. Taking it this side, so dk is equals to mav dt. Integrating both the side, this mass and acceleration are constant, so dk will be, let's say limit is from k initial to k final, so this will give us k final minus k initial is equals to ma is constant, so ma integration v dt will give us displacement. So k final minus k initial will be equal to change in kinetic energy. This mass into acceleration is force and this is displacement, but force into displacement is work done. So even for the variable force, the work energy theorem holds good. So delta K is equals to work done. Now let us see some examples on work energy theorem. In this example, the position of particle of mass 1 kg moving along x-axis at time t is given by x is equals to half t square. We want to find the work done by force acting on it in time interval t is equals to 0 to t is equals to 3 seconds. First, we will find the work done by the regular method and then we will use the work energy theorem so that you can compare both the methods. So method 1. The work done is force into displacement. We can find displacement between 0 to 3 seconds. From this equation directly we have to find the force. So force is given by mass into acceleration. Mass is given 1 kg. So our first task will be to find the acceleration. We have the position time equation, that is x is equals to half t square. Differentiate it with respect to time, we will get velocity is equals to 2 by 2t, that is equals to t. Again differentiating velocity with respect to time, we will get acceleration and dt by dt will be equal to 1. So acceleration is 1 meter per second square. So force will be 1 into 1, that will be equal to 1 Newton. Now we want the displacement. The position equation is given x is equals to half t square. We want to find the work done between t is equals to 0 to t is equals to 3 seconds. For t is equals to 0, x is equals to 0. And for t is equals to 3, x will be equal to 9 by 2. So the displacement will be, let's say this is final position and this is initial position. So displacement will be 9 by 2 meter. We have force, we have displacement. We can find the work done as force 1 Newton into displacement 9 by 2 meter, that is equal to 9 by 2 joule. Now we will find the work done using work energy theorem. So let us see the method 2, that is by using work energy theorem. According to work energy theorem, work done is equals to change in kinetic energy, that is equals to half mv square minus half mu square. We know the value of mass 1 kg. We have to find the final and initial velocities. We know the position equation, x is equals to half t square. Differentiate both the side with respect to time. We will get velocity that will be equal to t. So at t is equals to 0, initial velocity will be 0, and at t is equals to 3 seconds, the final velocity will be equal to t, that is 3 meter per second. So according to work energy theorem, the work done will be equal to half into mass 1 into v square, that is 9, minus half into mass 1 into initial velocity 0. So work done will be equal to 9 by 2 joule. So by both the methods we are getting same answer. You can use the method you are comfortable in. Now in this example, it is given that the velocity of a particle of mass m moving along x-axis is given by v is equals to b root 6, where b is constant. We want to find the work done by force during its motion from x is equals to 0 to x is equals to 4 meter. To find the work done, we can use work energy theorem, that is work done is equals to change in kinetic energy, that is equals to half mv square minus half mu square. The function of velocity is given as b root x. We want to find the work done from x is equals to 0 to x is equals to 4 meter. So initial velocity will be at x is equals to 0, put this value, so u will be 0. The final velocity will be at x is equals to 4, so that will be 4 b root 4, that will be 2b. So work done will be equal to change in kinetic energy, so half m v square will be 4b square minus half m u square will be 0. So work done will be equal to 2mb square. In the example, a string is used to pull a block of mass m vertically up by a distance h. At constant acceleration g by 4. It is shown in figure that block of mass m is hanged with the help of a massless string and it is moved in upward direction with constant acceleration that is equal to g by 4. We want to find the work done by the tension force. Here the tension force will be created in the string. If we draw the free body diagram of the block, then the gravitational force in the downward direction mg, tension force in the upward direction, and net motion is in upward direction with acceleration g by 4. If we write the equation for this block, then tension force will be more because ultimately the block is moving in upward direction. So T minus mg is equals to the net motion or net force of the block will be mg by 4. So the tension force will be mg plus mg by 4, that will be equal to 5 mg by 4. Now we want to find the work done by tension force, that will be equal to force into displacement. While it moves up, it is moving up by a distance of h, so displacement will be s. Here tension force is in upward direction and the displacement is also in upward direction, so the angle between them will be 0 degree. So work done will be tension forces 5 mg by 4 into displacement h into 1. So work done will be 5 by 4 mg h. So this will be our final answer. Now let us see one special example of variable force, that is the problem of hanging chain or rope. In the figure it is given that a chain is hanging over the edge of a table. In the statement it is given a chain of length L and mass m has uniform linear mass density. That means mass is distributed equally throughout the length. The length small l is hanging over the edge of the table. So this length is small l and the total length is capital L. What is the minimum work done required to pull up the hanging part? Here focus on the word minimum. If you have just asked the work done, then you can simply find the mass of this hanging part and the work done will be mg L by 2. But here we want the minimum work done. Now what will happen for the minimum work done? First we start pulling the chain in this direction with some force F. At that point this force will be equal to the weight of the hanging part. Now after some time some of the part is lifted up. Now the hanging part is reduced, so the force required will also be reduced. So to have minimum work done, we have to continuously reduce our applied force so that we can pull the chain in minimum work. So in this case our force will be variable. That's why it is the variable force case. Now let us assume a small part dx having mass dm. So first of all we will find the mass of this part. The chain is having uniform linear mass density, so small mass dm will be equal to m by L into dx. Now let us say at any instant x length of this chain is hanging and this x length is variable. So this is the length x and it is variable. To pull the mass of x length, we require the force F that will be equal to m by L into x, that is the mass of hanging part, into g, this is force. Now as we gradually pull the chain up, the force will be reducing, so the work done will be equal to integration F dot dx. Put the value of F in this equation, we will get F is equals to, we will get work is equals to integration m by L x into g into dx. Here m is the mass of the whole length and length L is the total length. M by L and g are constant, so work done will be equal to m by L g into integration x dx. Now what about the limits? Initially L part of the length or chain was hanging, and finally when the whole chain is pulled up, then the hanging part will be 0. Remember, here x is the hanging part. Integrating this, we will get work done is equals to m by L into g into x square by 2, limits from L to 0. So we will get work done is equals to m by 2L g into L square. The g is in multiplication. So writing the formula properly, W will be mg L square divided by 2L. This answer will be negative because we have found the work done by gravitation force. So minimum work done required, or minimum external work done required, will be plus. So mg L square divided by 2L. Here L is the total length and small l is the length of hanging part. So remember this formula as a shortcut. It will be handy to solve the problems. Now let us see one example based on the formula that we have just seen. A chain is on a frictionless table with 1/5 of its length hanging over the edge. If the chain has length capital L and mass m, then what is the work done? That is minimum work done required to pull the hanging part back onto the table. Here L is the total length and L by 5 is the length of hanging part. The minimum work done required to pull the hanging part is mg L square divided by 2L. Here small l is given capital L by 5, that is the length of hanging part. So this will be mg into small l is L by 5 whole square divided by 2L. So mg L square divided by 5 square 25 into 2 50 into L. And L will get cancelled out. So the minimum work done will be mgl by 50. So this will be our final answer. In this example, the kinetic energy of a particle moving along a circle of radius r depends on the distance covered as k is equals to alpha s square, where alpha is constant. We want to find the force acting on the particle as a function of s. Here, as the kinetic energy is variable, that means speed is variable. So it is the non-uniform circular motion. In the non-uniform circular motion, there are two forces acting on the particle. One is centripetal force towards the center. Here, as the speed is increasing, the tangential force will be along the velocity. So the net force will be equal to under root Fc square, that is F centripetal square, plus F tangential square. So now our task is to find centripetal force and tangential force. First, we will find the centripetal force. It is given that kinetic energy is alpha s square. So we can write half mv square is equals to alpha s square. At any instant, the centripetal force is given by mv square by r. From this, we can write mv square is equals to 2 alpha s square. So centripetal force will be mv square by r, that will be equal to 2 alpha s square. Now we want to find the tangential force. The kinetic energy can be given as half mv square is equals to alpha s square. Now differentiating both the side with position s. So we will get this half m is constant. So half m, differentiation of v square will be 2v dv by ds will be equal to 2 alpha s. But v dv by dx is equals to acceleration. This 2 will get cancelled out. V dv by ds is written as acceleration. So mass into acceleration is equal to 2 alpha s. This will be the tangential force. So Ft will be equal to 2 alpha s. We have found centripetal force. We have found tangential force. So the net force will be under root Fc square plus Ft square, that is equals to under root two alpha s square by r whole square plus Ft is 2 alpha s whole square. We can take 2 alpha s common, so this will be 2 alpha s into under root s divided by r square plus 1. This will be square. So this is our final answer for net force acting on a particle in non-uniform circular motion.